Exercise 4.2, question 10. So we are discussing the mean value theorem. So then let us try to answer this question. You have a function fx equals to 3, and then you have values of functions to be a parabola for x between 0 and 1, and then you have a straight line for the m that is between 1 and 2. So if you refer to the intermediate value theorem, just now someone is answered questions. I think Bing Chong or who is answered this question. It says the function has to be continuous. So you have to make sure that the functions is a continuous functions in order for the mean value theorems to be valid between the intervals 0 and 2. So you have a functions that is defined based on intervals of 0 and 2, and the functions is divided into 3 parts. And in the first part, when x equals to 0, the function has a values of 3. Right? So that is how you translate the functions into the forms of a graph. Then the functions between 0 and 1, it is a parabola. Right? So it's a parabola that is in the forms of x squared minus x squared plus 3x plus a for x between 0 and 1, and the function is equals to 3 when x equals to 0, and when x equals to 1, the values of the function is somewhere. Then for x equals between 1 and 2, the function is mx plus b, which means it is a flat line. So you can imagine the shape of the functions by using the informations provided by the questions. So the functions between 0 and 1 is a parabola. So the function has to be sketched on this part, and it has to be continuous. And on these sections between 1 and 2, the function is mx plus b. Okay, so a, b, and c are numbers which you don't know, but what you can know is the functions between 1 and 2 it must be a straight line, and then between 0 and 1 is a parabola. So the most simple way of representing these functions is by drawing a graph which is parabola. So the parabola can have a positive concavity, or can have a positive parabola or negative parabola. So if it's like this, then let me draw this. Let me clean off this part. So a parabola between 1 and 2 should be like this. Like this is a function of a parabola, ax squared plus bx plus c, and when x crosses 1, the function will become a straight line. Right? So the functions become a straight line, which is mx plus b. So it should be like this. So this is one way of imagining the functions. The other way of imagining the functions would be another one. So you could have a parabola where it is not a concave up but concave down. You could have a parabola that is also like this, ax plus b, and after it goes through x equals to 1, it becomes a straight line. So the straight line could be a straight line that goes up or goes down. It doesn't limit it. It could be like this, it could be like this. Right? So this is how you can imagine the functions. The important thing here is that at this point, the function has to agree on each other when x tends towards 2 from the left and x tends towards, the values of the functions have to agree when x tends to 1 from the left, which is this one, and also when x tends to 1 from the right. So this is an absolute requirement in order for the piecewise functions to be continuous. Now, once you understand this idea, then you should be able to complete the questions of what is the values of a, b, and c. Right? So let's see how you do that. So the function f is equals to 3, minus x squared plus 3x plus a and mx plus b. Right? When x equals to 0, x between 0 and 1, x between 1 and 2. So the first thing you would have to do is to try to accommodate the first piece of information, that is fx equals to 3 when x equals to 0. So the function I have mentioned has to be like this. This is a point here, and then it's a parabola somewhere here, and then become a straight line afterwards. So at this point, x equals to 0, and the point x equals to 1, the function has to be continuous, right? So let us try to encode these informations for this point using the functions. So you required the functions at x equals to 1 to be the same when x tends towards 0 from the right. So this is a situation of x tends towards 0 from the right. So what you require is that then this part of the function is a parabola functions. That is, when x tends towards 0, the limit of the function has to agree to be 3. And this is an x squared plus 3x plus 9 is a polynomial. Right? So the polynomial is known to be continuous. So the values of the function of the polynomial and the limit of the polynomial at x equals to 0 is the same. So you write down this. F at 3 must be equals to 3. And this should agree and apply to the polynomial. So the polynomial would be like this: 3 squared plus 3 plus a must equals to 3. So this is the first statement that allows you to solve the values of 3. Right? So this is minus 9, and this is 9. Sorry, this is a. Right? So here you can solve this one. So if I do not do it wrongly, then the constant a is 3. Based on simply requiring the functions to be continuous at the point x equals to 0. Right? So to obtain this point again, what you require is that the functions, let me write it down somewhere. I need a place to write down. That is, at this point of the functions, a polynomial of this, the limit of the functions when x tends towards 0 from the right, it must agree with the values of the functions at this point, which is 3. Right? So basically, I'm employing these conditions to the point x equals to 3. That is what I have. Then I conclude by using these conditions, the values of a is now known. So I have solved the constant a. So if it's the exam questions, then this allows me to get half of the marks. So now the next is to obtain values of b and m in the other part of the graph. So now let me clean off. I need to clean off. Okay. So the next bit I need to do is to look at the values of the functions. This is 0, which we already done. This is 1, and this is 2. And the functions at this point here is the values of the function at 1. Are you still there? Can you listen to me? Excuse me?
Yes, we can.
Yes,
Yeah,
sir.
okay. I think there's something wrong with the screen. It got stuck somewhere. I think, yeah, I think the screen got stuck. I have to close the WebEx and then switch on again. There's an error on that. Okay, wait for the program. There's a lot of error this morning. So I have to close and then come in again. Sorry about that. Okay, so I think there's some problem just now. I have to start my WebEx and admit everyone over again. Okay, so are you still there? Everyone can hear me?
Yes,
Can you
doctor.
hear me? Yeah, okay, good. Okay, fine. So let me come back to my screen. Okay, so I was talking about this part. Now we have a functions at x equals to 1 and x equals to 2. So I have a equations that connects the quadratic functions and the straight line. So imagine you have a straight line between 2 and 3. So here for x between 1 and 2, not 2 and 3, the function is mx plus b. So that is the red color line. And between the 0 and 1, for x between 0 and 1, the function is a parabola, which is minus x. Okay, so you have a parabola minus x plus a. So I think if this is a parabola with minus x squared, the function should be something like this, right? So, and then it must get to the values of 3. So so the parabola should look something like this. I think this is the correct way. Just now I draw it in a different way because I thought that the parabola, just now I thought the parabola is like this, but because I didn't realize that the shape of the parabola it has a minus sign here. So if it's minus sign, then the parabola must be like this one. Okay, it must be like this one. So it start off with 3 and then it end up with somewhere here. Then you have this parabola, and then you have this bit. And now it's quite straightforward to apply the boundary, so-called boundary condition at x equals to 2 and x equals to 1. Okay, so let me write it down here. You have at x equals to 2, x equals to 1. So at x equals to 1, the functions of the function fx for x goes to 1 from the left must be equals to the limit of the function fx when x goes to 1 from the right. Right, so this is the statement I will write down to connect the functions at the point x equals to 1. So when x goes to 1 from the left, it is referring to the behaviors of these functions. When x tends towards 1 plus from the right, I am referring to the straight line from the right. So now you can then translate equations and translate these statements then by writing down the left hand side for these statements is just equals to the values of the parabolic functions at x equals to 1. Right, so the left hand side statements would then be translated into x squared plus 3x plus a, where the values of a has been calculated just now. I think it's 9 or something like that. So that is the left hand side of the limit. It must equals to the right hand side of the limit, which is this part. So when the function goes to the 1 from the right, I am referring to the straight line, which is mx plus b. Okay, so this is one equations, and that x has to be replaced by 1 because we are talking about the limit of x goes to 1 from both left and right. So you just simply replace x by 1, and then you replace this by 1. So that is and this is also 1. So this should be minus 1 minus 1 plus 3 plus 9 equals to this plus a. So this would be then a plus 2 equals to m plus b. So mind you, in these equations, A has been obtained when we analyze the behavior of the function x equals to 3. Now, for those who are having other commitment or lecture, you can go to other parts. You can just leave now. You are not needed to remain in this class. But for those who still want, I'll continue to discuss the questions until maybe 1 o'clock. So this will be the extended discussion sessions, not on lecture, but discussing the questions. So so it's okay if you just leave. If you want to stay back, it would be good. Okay, so now I have come to the situations where I have formed an equations of a plus 2 equals to m plus. So here m and b are not known, but I have already got the equations that describe m plus b. Okay, so then what I'm going to do is that I proceed to look at the equations, and x is located at 2. So again, according to if you want to apply the mean value theorems, the function has to be continuous. So for the functions to be continuous at 2, again, then you require the functions fx, the limit of the function x goes to 2 from the left must be equals to the values of the function at 2. Okay, so that is what happened to 2. So the function at x equals to 2 is mx plus b. Let me see the questions again. Questions do not give me the values of b. So now I have a slight problem to proceed. I have only one equations, and I need to solve for the values of a and b. But I couldn't find the values of a and b. Sorry, a is already known, so I need to find out what is m and b. But I have only one equations. So I was thinking maybe by applying the theorem of continuity at this point, I should be able to work out another equations so that I can use it to solve for m and b. But it doesn't look like it because I do not know the values of the function at x equals to 2. Let's see what happened. When x equals to 2, the function x equals to 2 from the left is equals to 2m plus b. Okay. So you have values of the function at f equals to 2m plus b. But how could you make use of these functions to calculate the mean value theorem? So the mean value theorem is supposed to be a hint for you to work out the values of fa and fb. So I do not know how to proceed with this at this point. So what I have done so far, so
Doctor,
any
is
suggestion?
because the mean value theorem only works if all the points are differentiable. So that means the gradient of the function at 1 has to equal the from the left have to equal from the right.
Thank you very much. So Bengi is speaking. Thank you very much for so now let me repeat again what I said. Just now I was thinking I should make use of the point of the function at x equals to 2 in order for me to work out. Therefore, I write down this one equation. But it turns out that this is actually a wrong strategy. I should not consider this. So this is a wrong considerations. So just like you thought it should be solved according to this method, but then realize that no, this is not the correct way. So the correct way is to look at the intermediate value problem at x equals to 1 and require that the function has to be continuous. So the functions has to be continuous. It has to be continuous. Not only continuous. So the function requires the theorem requires the functions to be differentiable at the point x equals to 1. So we use these statements that the functions must be differentiable at x equals to 1. So that is the applications of the mean value theorem. The mean value theorem requires a function to be differentiable at every point in the function. So it must be true also at this point. So before I proceed on to solve the problem, I think I have done another stupid mistake. Not really a stupid mistake. The functions should not have a king if it's to be differentiable. So if I were to draw this again, I wouldn't draw the function to be like this. I should draw the functions to have a derivative that is continuous as well. That is, if the function happens here, then the slope must be continuous. I think that is a more appropriate way of drawing the functions. So if I draw it like this as well, then there will be a king, like a sharp point that will make that function not differentiable. So it's a wrong representation when I draw the function to looks like this and have a sharp king. The correct way should be a parabola like this, and then it will continue on with the same slope. So with this understanding, then we are able to write down another equations. We'll be able to write down another equations to we will be able to write down another equations to solve for that, right? So set at x equals to 1, the functions has to be differentiable. That is, f prime for the functions when x tends towards 1 from the left must equals to the derivative of the functions when x tends to 1 from the right. So that is a more appropriate functions. So when x is on the left hand side of the equations, the functions is minus x squared plus 3x plus b. And when x is on the right hand side of 1, the function is mx plus b, right? It's mx plus b. So this is the function on the left, this is the function on the right. Therefore, the statement that the derivative of the functions from the left of 1 is then equals to just 2x plus 3. And you have to set the x of going to 1 from the left. Then on the right hand side, the derivative of the function is referring to m, right? So it's equals to m. So in other words, the values of m is just equals to these expressions, and you set x tends to 1 from the left. So whether the x tends to 1 from the left or from the right, this will just give you 6, right? You just substitute x by 1, then you have 2 times 1 plus 3, so it's 5, not 6. So I have another equations that has been solved. M is just equals to 5. And earlier on, when I consider x equals to 0, I have already obtained x a equals to, I don't know, 9 or something. Then I also write down another equations that requires the functions to be continuous at
Doctor,
the point.
it should be negative 2x plus 3 because
Negative 2x, yeah, sorry, negative 2x plus 3. So m is equals to 1. Okay, thank you very much. So that is my mistake. Okay, so m is equals to 1. Okay, so these are algebraic mistakes which you should not make, but I always make it, right? Because I have to explain to you, so I get confused very easily in front of the screen. So anyway, we have values of a, which is already solved. The slope has been solved. Now the b, right? So the b has been solved can be solved as well by referring to the previous slide, which I already write off. I think just now the requirement is that the function at the point x equals to 1 has to be continuous. So the functions at x equals to this one is equals to minus 1 plus 3 plus a is equals to the values of the functions from the right, which is m plus b as well. So m has been calculated, a has been calculated, 9b could then be easily calculated. So again, this is a question which is asking you whether you understand or not the applications of the intermediate of the mean value theorem. That is, you have to know that for the mean value theorems, the function has to be differentiable. In particular, the function has to be differentiable at the point of x equals to 1. So that would allow you to write down one equations. Then you require the functions to be equal to 3 at x equals to 0. That allows you to write down another equations. Then another equation, it will be the requirement that the function is continuous at x equals to 1, differentiable at x equals to 1, and the function at x equals to 0 is equals to 3. So this will allow you to write down 3 equations, and 3 equations would then allow you to solve for a, b, and m. So that is how you solve these questions. Okay, so that is it. Applications of mean value theorem. When we talk about the mean value theorem in the lecture, it's very straightforward. A mean value theorem is like this: you have this function between this and that, blah blah blah. But the assumption behind the mean value theorem is it is differentiable throughout the domain, and differentiability also infer continuity. So this question tests you whether you know how to apply differentiability and continuity at the intermediate point of x equals to 1. So that is the gist of the questions. Okay, so it's already 12:12. We have 3 more questions to go. So I'll take a break here. For those who are still interested to stay, you can stay. Maybe I'll take another maybe half an hour or maybe 45 minutes to continue talking about the questions. I'll stop recording here for the moment. So now we are going to discuss another questions, last questions on exercise 4.5, question 40, Fermat principle in optics. So I think this is an applications of optimizations. See if this, I think this could be a little bit complicated, but this is a questions which is kind of difficult to do because it doesn't have any equations. So questions that has not equations and requires your interpretations sometimes could become quite difficult, because it's really not testing your understandings of mathematics, but test your understandings of physics. It also tests you on see how if you can put every pieces, all the facts down into the forms of a mathematics. Fermat principle in optics states that light always travel from one point to another along a path that minimizes the travel time. Light from a source A is reflected by a plane mirror to reflect to a receiver at point B as shown in the figure. It shows that for the light to obey Fermat's principle, the angle of incidence must equal the angle of reflection. Both measure from the line of normal to reflection surface. The result can also be derived without calculus. This is purely geometrical argument which you may prefer. So here you have a questions that you have to show the time. So you have to write down equations that describes the time. So and also you have to translate these questions into mathematical form. So how we're going to do that? Let us try to understand it. So first of all, imagine you have a light source A. It hits to the point here, and then it's reflected to a point B. So there is a distance from point A to the reflection point, or reflection point to the receiver. And then you have to write down an equation that describes the time from point A to the reflection point, and from reflection point to point B. So you sum up the time from A to reflection point, and the time from point of reflections to point B. Then you have to understand the time from A to plane mirror is closely related to the angle, right? So imagine if the locations of light source A changes up a bit or down a little bit, then the angle here would change as well. And the reflections from here to here is given by this length. The length also depends on two factors, that is the height of the bee and also the position of the bee along this horizontal line. So what I'm trying to tell you is that the time from A to the plane mirror is dependent on what this angle is. So the angle A, θ1, will decide how long the time take for light to go from A to here, and that θ2 will decide how long the time take for light to travel from this point to this point. Then you form their functions for the time t1 plus time t2. Then you would minimize the angle. Well, you minimize the time taken as a function of the angle. So finally, what you have to prove is that the θ1 and θ2 have to be equals. That would be the requirements so that the time taken from A to B is a minimum. So here, θ1 and θ2 are two so-called independent variable. Initially, you assume θ1 to be an independent free parameter, θ2 to be another free and independent parameter. θ1, θ2, they do not tied to each other, they are independent. Then by applying the optimization problem, that is to require the time taken from A to B is a minimum, then you expect the answer when you minimize it is that θ1 must be equal to θ2 in order for the minimization to occur. So this is a question of a proof. Before you can prove it, you already know what you should show. You should show finally θ1 must be equal to θ2. Right. So that is the Fermat's principle. Let's see if we can do it. I would like to share it on my screen. Okay. So I go to my share screen. Okay, I need a whiteboard. So the geometry of the questions is quite straightforward. We have I call it point A, and I call it point B and point C. Right. Then the point B and point C are three arbitrary points, which is described by θ1 and θ2. So we need to define, say, the length, say L1. L1 is the length of AC, L2 is the length of BC, L2. Okay. So the time taken for the light to go from A to C can be easily written down as a length of L1 divided by the speed of light. So is the time t2, is the time taken for light to go from C to B. It is the length of L2 divided by the speed of light. So C is the speed of light. It's a constant. So you learn ZCA, ZCT 104, then this is a usual equation that you write down when you study special theory of relativity in the second semester later. So the total time t is a functions. Well, wait, before we proceed on, then we would like to translate these equations into theta. So somehow this angle must be related to the theta. So how am I going to relate this to the theta? So L2 theta. Okay, let me look at the questions again. The question says along the path that minimizes the travel time, light from source A reflected by point to point B, the angle of incident, both the measure from the line normal diffraction angle is the same, can also derive without calculus. Okay, so now I have to think of how to get the light going from there to there. Okay, so I am get stuck at this point. No, I think also the questions, the angle of theta1, theta2 is not measured like this, but it's measured as theta1, and this is theta2. Okay, so so let me resume. Now I will try to solve this again by looking at the triangle. So the triangle that I'm going to talk about is a triangle that is formed by A, B, and C. So I have a triangle ABC, and see if my attempts would lead me to a correct solution. So the length of AB is related to L1 square plus L2 square plus 2 L1.
Doctor, if you see the question, it's not always. Oh, wait, never mind. Sorry, never mind.
Yeah, never mind. Thank you for anyway for your suggestions. So okay, I'm trying to use the cosine functions to do this. L1 square plus L2 square plus 2L1 L2, and then this is cos theta 1 and cos theta 2. So this is the time of a square b square. But do I get anything out of this as my problem? I have to somehow get L1 and L2 to be related to the time and the cos theta 1 and to the theta 1 and theta 2. No, I couldn't think of the correct solutions. Bingy, you have any suggestions for me?
No, I thought wrong. Never mind.
So the height of A and B are not really fixed. Here, the distance of A to B and B to A, they are not supposed to be of the same height. But can I make them to be of the same height? Now, if they are made to be of the same height, then maybe there is a way how I can solve these equations. So at this point, let me explain what I'm thinking. I'm just showing you the process of my thinking. I can't proceed on because here the height of B from the plane and the height of A from the plane is supposed to be arbitrary, like they are not assumed to be of the same distance. Okay, so they are not supposed to be from the same distance. But let's say if I make a further constraint that A and B, they are of the same height from the plane. So maybe that would help me to solve this problem. So that is just my attempt of solving. I just try to reduce the numbers of free parameter from the problem by imposing this additional condition. But I think in general, H1 and H2 in general, they are not the same. But let's say if they are the same, can I still prove the Fermat problem? Maybe I can. Now let me try to explain myself. So you have a plane, you have a point at the same height, then it's a point A. Then the point A shines a light onto here, and then it forms an angle of theta 1. And this is a point A, and you have a point C. Then another height of B is somewhere here. So in general, the B could be located any horizontal distance from C and form another angle of theta 2. So that is different slightly from the general situations where the B is located at a different height. or at here, right? So, but I would just continue to assume that the B, oh, okay, so wait, I got problem with my rubber. So I think it should be okay if I assume the height of A and B to be the same. Okay, so let's see if this is going to help me to solve the Fermat principle problem. So if this is the same, so I assume L, I call this H, okay? So H to be a constant. So again, I label here as L1 and L2. Then L1 and L2, they are related. That is tangent theta 1 is equals to, not tangent, I think it's sine. So again, I have a relationships that relates cos to the L and H. That is cos theta 1 is then equals to H over L1, and I have cos theta 2 equals to H of L2. Or in other words, if I were to express this in terms of H, then the H on the left and the right would be same. Okay, so I assume then H is just equals to cos theta 1 divided by L1 equals to cos theta 2 by L2. Okay, so that would be my first equations that I write down in my proof. Then the second equations that I'm going to write down would be the time, right? So the T1, as I mentioned, is the length L1 divided by C. So the time T1 is this. T2 is equals to the length of C as well. So my functions T is T1 plus T2. So let's see if I can form this function. So T1, T2, it would be then L1, L1 plus L2 divided by C. Okay, and then I'm going to translate my L1 and L2 into the forms of a cos theta. So here, okay, so I need some space. Let me clean off the space here. Maybe I feel like I am in the right directions, I think. Okay, so I'm going to continue writing my T to be in terms of 1 over C. So I write my C on the left hand side. So I have only L1 plus L2. So from these expressions of this one, these equations, then you can make L1 to be equals to L2 times cos theta 1 divided by cos theta 2. Okay, so that is what I'm going to do. So I'm going to write L1 plus L2 as L1 as L2 1 plus cos theta 1 and cos theta 2. Okay, I think more or less I have done it. So L is the length which is held constant, and theta 1 and theta 2 are something which is varying. So here the values of the total time for the light to travel from A to C and C to A is just given by L2 times C, which is a constant, times a factor of 1 plus cos theta 1 over cos theta 2. And in doing so, you assume that the length of L2 stays constant. The only thing that changed is the time taken, right? So L2 is constant, L1 is constant, the H is constant. Only theta1 and theta2 are two variables. So now you can imagine that this is a values for the function t, the time taken for the light to travel, and it depends very much on theta1 and theta2. So you further assume one of the theta is constant, right? So for example, you make theta1 to held constants, and then you only varies theta2. So imagine that you have a function t based on, say, cos theta 2, and you choose the theta 1 to held at constant. Right? So when theta 1 and theta 2 is, so when theta 1 is held at constant, theta L1 and L2 are also held at a constant. So is the values of the height. They are all held constant, but only allow cos theta 2 to vary. Then you would have a kind of constant functions, which will be like something like this, plus constant of 1 over x. I think it will be, not sure, I think it will be something like this. I'm not exactly sure, but generally you expect the t to be function of cos theta 2 to be like that. And then you will assume that at the point where t is a minimum, the values of cos theta 2 is equals to cos theta 1. Okay, so here you assume cos theta 2 to be variables, then the variable will be varies. When it varies, the values of the time travel for the light source from point A to B would hit a minimum when the variable cos theta 2 is equals to cos theta 1. Wait, pause for a while. Okay, so so now I have a situations like this. Let me proceed to see if I got it right. I'm not going to make theta 1, theta 2 as my variable, but I'm going to make cos theta 1 and cos theta 2 instead as my variable. And I'm going to differentiate with respect to cos theta 2 instead of differentiate with respect to theta 2. Okay, so that is what I would expect when I minimize the function of t, I would get the solutions to be such that cos theta 1 is equals to cos theta 2. Okay, so I will proceed to check my hypothesis and see whether my method works. If it works, then I'll get the correct answer. If it doesn't work, then I would not get my correct answer. So here I assume cos theta 1 is a constant, and I call this constant and just give it a name. Maybe I call it Q. So I have L1, L2 constants. So this is another constant, and I would call Q, I call this Q1, which is constant. I call Q2 to be cos theta 2. Okay, so by doing that, I'll be able to express the function of t in terms of some constants, L2 over C as 1 plus Q1 over Q2. So here I assume Q1 to be a constant. So now what I'm going to do is that I'm going to differentiate dt dq2, because dq2 is in variables. I make theta 2 as my variable, so q2 is my variable, and see what I got. So I'm going to set this to 0 and then minimize it. So that would give me a constant of L2 over C times Q1 with a minus sign of Q2 squared. So that is my first derivative. So when I set it to be 0, then it would not be accurate. It will not be correct, because in that case, Yeah, in that case, I would not get anything because by setting dt dq2 equals to 0, the only solutions I get is q1 equals to 0. So that would not give me any correct answer. So it looks like this is not a good try. So at this point, I have failed my attempt to find the correct way to prove the format principle. Okay, so the answer is up to this stage, my attempt fails. So I'll stop recording here for a minute. Okay, so the way how I solve this doesn't seem to be correct. The correct answer for the solution should be referred to this graph. So you construct the shape of the light from A shine to point T, and then from point T you goes to B. So this is a geometry, and you have the angle θ1 and the angle of θ2. Okay, so it is clear from here θ1, θ2, and they call this alpha, we call it beta. So the height of A from the plane of mirror is A, height of B from the mirror is B. So this is the geometry constructions of the Fermat principle problem. Okay, so then what it says here is that it look at the distance of OT plus TB. So OT is from, okay, now I understand the questions. So A will goes to T, the light, then the light from T would goes to B. So in order to make your calculation more convenient, you just reflect this triangle. This is upper triangle of AT onto the plane of the mirror, so that A is reflected onto O. So instead of looking at this light, yeah.
Sorry, Doctor. Doctor didn't share your screen. Please.
Oh, okay. Thank you very much for telling me that. Okay, I have to share my screen.
Okay, Doctor.
Okay. Yeah, sorry. The screen I'm looking at is the solutions. The solutions from the ISM. I think the file is this C04G PDF. Okay, so this is the solutions. It constructs the geometry of the light source from A to T and from T to B. Right? So and this is angle θ1 and θ2. So the questions, in order to make it easy to solve, it reflects the point A to point O. So that is exactly the same triangle, but flipped over to O and T instead of A and T, so that you have a straight line from O to T and from T to B. So you can imagine the reflections is not from A to T to B, but from O to T to B. So that is equivalent, like it's exactly the equivalent form of going from A to T and T to B. So now you look at OT plus TB. So the question is that you should try to minimize the time taken from O to T and from T to B, right? So you look at this one. So you sum the distance from O to T and from T to B. And of course, the time taken for the light to go from O to T and from T to B is just equals or just exactly rely on the distance. The larger the distance is, the time is longer. I also already mentioned in the previous slides, when I write down the time taken is just the length divided by the c, right? So the time taken for traveling from O to T and T to B is just directly proportional to the length from O to B, which is the sum of OT plus TB. So that explains the distance minimized. So when you minimize the distance, that is amount to minimize the time. I think that is what that solution says. In order to minimize the time, you just minimize the length. Right? So how do you minimize the length? It says the minimized length, the length from O to T and T to B is minimized when OB, that is from here to here, is a straight line. So in general, the alpha angle, which is related to theta, is sorry, let me say it again. In general, θ1 and θ2 is not the same, right? So but you can express the angle theta into the forms of alpha. Right? So alpha is just a complement to theta. Alpha is just 90 degree minus theta 1. So you can imagine this alpha is just an proxy to theta 1. Right? So theta alpha is just 90 degree minus theta 1. So you have beta, which is just a complement to theta 2. So you look at this triangle. In general, theta 1 and theta 2 are not the same. That also translates into the fact that alpha and beta are not the same. So if alpha and beta are not the same angle, then the length of 0 to from O to T and from T to B would not be of the same line. So maybe I can scribble it here using the scribble. I think we are almost done with that. So you have a point here. So in general, the angle alpha and the angle beta are not the same, right? If they are not the same, then you can measure the length from O to T, from T to B, right? So basically, it's just this length plus this length, right? So based on very simple geometry, the length or the sum of the length L1 plus L2 would be always larger than the length of L1 plus L2 prime, where L2 prime is the length of the B when it is like this, when the beta is equals to alpha. Then this will give you the length of alpha 2 prime. Now what I'm trying to say is that a length that is like this and this will always be larger than the length of two lines but aligned together, right? So this, if it's not strict, the total length will always be larger than the length that is constructed of these two sections of line, but the two lines, they are all lined up equally of the same directions. So I think that is the argument that is mentioned by this Fermat-Rush principle. So it doesn't really make any minimizations procedure. It just use geometric argument to say that you want to minimize time, you minimize the total length from O to T and from T to B. So the total length from O to T and from T to B would be a minimum if the angles of this line segment OT and OB, they are of the same angle. Right? If they are not the same angle, they will not be aligned. It will be aligned. Then the sum of the length will be always less than the sum of OT and TB when the alpha and beta are not the same. So that is how they make the argument for doing this. So in a way, the solutions does not provide a procedure of minimizing the functions of the time. It just use geometrical argument to solve the problem. And this is a physical way. Physics people would do that instead of just write down the equations. But when I solve the question in my previous attempts, I'm trying to translate this question into an equation for which I can't minimize it. But obviously, I failed. But I think there must be a correct way. There must be a correct way of minimizing this problem, the time, and arrive at the angle θ1 to be equals to θ2. Okay. So I think the solution provided by me is not exactly satisfactory. But at least I tried. Okay, so you can try it yourself. Benny, if you are interested, then you let me know if you have your own solutions so that we can discuss this with the class as well. Okay, so it's already been very late, 12:55, so I'll stop my recording here now. Okay, so any questions before we start? We stop the sessions. It's been 2 hours of discussion, lengthy discussions. No. Okay, so if there's no response from from the participants, then we'll end our meeting here. That's all for today. Okay. Okay, thank you for
Thank you,
your
Doctor.
sure. Thank you for your patience to go through all these difficult discussions with me. It must be very boring to you. But I think the people who stay back finally are people who really show keen interest to learn the mathematics. Okay, those people who just jump early on, maybe not really interested in the physics stuff. Okay, that's all for today. I'll see you 2 weeks later. I'll let you inform when I finish preparing the tutorial questions and also the other 4 offline lecture. Okay.